So our first speaker is Joe Miller, who is going to talk about introenumerable sets and the cototal enumeration degrees.
Okay, thank you. Yes, as my title says, I'll talk about the introenumerable sets and their relationship to the cototal enumeration degrees. I'll start with a brief review of the enumeration degrees. I know this won't be the first one given this week. I think Junle gave a good overview earlier in the week. And then I'll talk about minimal subshifts, which was our original motivation for setting the cototal sets and degrees. Emmanuel Jindel sent us an email asking about this property, and we didn't really know anything about it. But in that email exchange, you also mentioned uniform introenumerability. So the two notions were already linked from the beginning. I'll talk then about enumeration pointed trees and McCarthy's characterization of cototality, and I'll relate that to uniform introenumerability. And then near the end, I'll start talking about, or maybe the middle, I'll start talking about my recent work with Junle, Josiah, and Maria on all of these notions. Near the end, I'll talk about the proof that there is a uniformly introenumerable set that is not of cototal degree. Hopefully by that point, it'll be at least somewhat motivated. Okay, so let me go through an introduction to the enumeration degrees, which, like I said, I think you've probably seen a similar introduction already. They were introduced in 1959 by Friedberg and Rogers. And informally, A is enumeration below B if there's a uniform way to enumerate A given any enumeration of B. The uniformity can be removed, actually, and you get the same notion, as it turns out. Or to put that differently, the uniformity comes for free. The more formal definition, which is really equivalent, to any reasonable way you would formalize this. But the usual definition we give is that A is enumeration below B if there's a C set of what we call axioms. These are pairs N, E, where N is a natural number and E is an index for a finite set, such that A is a set of all N such that some axiom in W, N, E, such that the finite set D sub E is a subset of B. So as we see B being enumerated, we see suddenly, DE is a subset of B, therefore I can put N into A. The degree structure induced by enumeration reducibility is called the enumeration degrees. It is an upper semilattice with least element, the degree of all CE sets. Okay, and it has a nice relationship to the Turing degrees. You can think of the enumeration degrees as being the reduction that takes positive information about a set B and gives you positive information about a set A. But if you code both the positive and negative information about B as positive information by taking the B join B complement, and the same for A, well, then it reduces to Turing. Then it becomes Turing reducibility. A is Turing reducible to B if and only if A join A complement is enumeration reducible to B join B complement. All the information in A and B are now being treated as positive information, so we have access to both the elements of A and the elements of A complement, and same for B. Well, anyway, this gives us a nice embedding of the Turing degrees into the enumeration degrees, which just takes the Turing degree of A to the enumeration degree of A join A complement. This preserves order, preserves the least upper bound. So we have an embedded copy of the Turing degrees inside the enumeration degrees. A set A is called total if A complement is enumeration below A, or if equivalently A is actually equivalent to enumeration equivalent to A join A complement. Now remember, these things with the form A join A complement, the degrees of these are in the range of this embedding of the Turing degrees. So what we get is that the total enumeration degrees, those that contain a total set, are exactly the Turing degrees, the image of the Turing degrees under the embedding iota. Okay, so we have the enumeration degrees, they have an embedded copy of the Turing degrees, we call those the total degrees for historical reasons. It's easy to prove that this substructure is definitely smaller, that there are non-total enumeration degrees. And for example, you can just take any sufficiently generic, a 1 generic, in fact, is sufficient. Okay. So that was a quick introduction. Hopefully, since you have seen that before, nothing will have come as a surprise. And so now to this email from Emmanuel Gendel. He asked, if A is enumeration below A complement, what can we say about the enumeration degree of A? And this email inspired a paper on these enumeration degrees, paper with quite a few authors, Andrews, Ganchev, Kuiper, Lemp, me, and Soskova and Soskova. I won't say much about that paper, but yeah, we went off and studied these degrees and some related notions. We call a set cototal if it has this property that A is enumeration below A complement. And notice that makes sense because remember, a set is total if A complement is enumeration below A. The cototal sets are just complements of total sets. The cototal degrees, on the other hand, are different. They're a little bit bigger than the total degrees. An enumeration degree is cototal if it contains a cototal set. And so I didn't write this down, but total degrees are cototal, and cototal degrees still form a proper substructure of the enumeration degrees. It's actually an interesting substructure. It's dense in the sense that between any two cototal enumeration degrees, there's another cototal enumeration degree. Any two comparable ones, there's another, there's another one. We proved a lot more about cototal degrees, but like I said, not necessarily relevant to this talk. Let's talk about Gendel's interest in these enumeration degrees. Well, in the enumeration degrees of sets with this property, and his interest comes out of symbolic dynamics. So that's what I'm going to get into a little bit right now. Okay. So the shift operator is the map on infinite binary sequences that just erases the first bit of a given sequence. A subshift is a closed shift invariant subset of Cantor space of 2 to the omega. Okay. Closed topologically, shift invariant, meaning, well, it means slightly more than what I'm about to say, but it implies that any element of C, if you take the shift of that, it's still in C. C is minimal if there's no non-empty proper subshift. And the language of a subshift is a set of finite binary strings that occur as a subword of some element of the subshift. Okay. Now, usually when you talk, if you've ever seen any symbolic dynamics before, the focus is not on the language of the subshift. It's usually on the complement of the language, the strings that are avoided. But today we'll be focusing on the language because there's a nice relationship between the language. Well, for minimal subshifts, the language is a sensible thing to look at. Actually, we'll be focusing on both the language and its complement. So the following are equivalent for a subshift C. C is minimal. It has no non-empty proper subshift. If you take any x in C and look at the sigma orbit of x, so you start taking shifts of x and look at that orbit, the closure of that orbit is all of C. The orbit is dense in C. And the reason for this, by the way, the reason for this equivalence is basically just that if you take the closure of any orbit, you get a subshift. Now that can't be a proper subshift. It must be the whole thing. So that's one direction of the equivalence there. And every x in C contains the same subwords. And this is really almost just a restatement of 2.
So excuse me, there is a question.
Oh, yeah. Subwords can appear anywhere, but since we're looking at the shift operator, actually doesn't matter, because if a subword appears anywhere and we take the shift of that, we get another element in the subshift. So it would actually be equivalent to look at initial segments. Good question, though. Yeah, so every X and C contains, well, it's important now for this last statement that every X and C contains the same subwords, that we don't just mean initial segments. And the reason is the subwords are the initial segments of the shifts of X. So if X is dense in C, it has to hit all of the places that, all of the places that that any other element of C can go, all the neighborhoods that any other element of C can go into. Well, those neighborhoods are exactly the subwords of those other elements. So all of the elements have the same subwords by 2, basically. 2 and 3 are really just saying the same thing in very different ways. Okay, so, but this is important. Minimal subshifts, every element contains the same subwords. So assume the C is minimal. Every X and C can enumerate the language by what I just said. Conversely, if I can enumerate the language, I can compute an element of C by, well, I just, I take the first subword I see, and then I start growing it as I see that I'm allowed to. So a Turing degree computes a member of a minimal subshift if and only if it enumerates the language of that minimal subshift. All right. And in fact, Schindel and Vanier in 2013 proved that for any non-trivial minimal subshift C, any Turing degree that computes a member of C actually contains a member of C. So the degrees of the members, non-trivial here means infinite, actually. The way it's defined. The degrees of members of this minimal subshift are closed upward, and they're exactly the degrees that enumerate the language of the subshift. The degrees of members are exactly the total degrees above the enumeration degree of the language. So this is what brings enumeration degrees into it. What about cototal enumeration degrees? Well, Schindel proved that if C is a minimal subshift, its language is a cototal set. In other words, its language is enumeration below the complement of its language. Let's sketch that proof. If we start with the full tree 2 to the less than omega, and we have an enumeration of the complement of the language, well then, as we see that strings are not in the language, we can just start killing off all branches that contain that as a substring. So forbidden words, we just forbid them. We prune the full tree. And by compactness, if tau is in the language, we already know that if tau is in the language, it's a substring of every path through the tree. By compactness, at some stage in this pruning, tau will be a subword of every current path, unpruned path. So it's just a simple compactness argument. We'll eventually see that tau is in the language because it'll be in every string that's left while we do this pruning process, every path that's left while we do this pruning process. A very similar compactness argument shows that if C is a minimal subshift, then there's an enumeration operator gamma such that for every infinite subset of the language, gamma of S is the whole language. So from every infinite subset of the language, we can enumerate, what I'm saying is true, but not quite what I have written down here. We can enumerate the whole language, or the language is uniformly enumeration below every infinite subset of itself. We say that the language is uniformly introenumerable. Now, why is this true? Well, every sufficiently long word in the language has to contain, so if tau is in the language, then every sufficiently long word in the language contains tau as a substring. So all we have to do is wait until we see tau as a substring. That's all that gamma is doing. It's just enumerating all the substrings of the strings in S. Okay, so like I said, these two notions came up around the same time. In this email exchange with Schindel, he said, what can you tell me about these kinds of sets, the enumeration degrees of these kinds of sets, because he cared about the spectra of minimal subshifts, the degrees of elements of minimal subshifts. So he wanted to understand the enumeration degrees of these kinds of sets. And he also mentioned, by the way, these minimal languages have this nice introenumerability property. Okay, so where are we at this point? Well, we are left with the following questions. Are the degrees of languages of minimal subshifts exactly the cototal degrees? I mean, it was our motivating example, but they might be special. And how do the uniformly introenumerable degrees, those that contain a uniformly introenumerable set, of course, relate to the cototal degrees? And I initially thought that the languages of minimal subshifts would be special, because I didn't see any reason why cototal degrees would be uniformly introenumerable. I thought that was the wedge we could use to separate the two, the two notions, to see that there are cototal degrees that don't contain the language of a minimal subshift. I was wrong, and my student Ethan McCarthy showed that every cototal enumeration degree is the degree of the language of a minimal subshift. So in fact, all cototal degrees are uniformly introenumerable. Not all cototal sets are, but all cototal sets are enumeration equivalent to, in fact, a cototal set that is also uniformly introenumerable. Now, McCarthy's proof passes through the notion of E-pointed trees. So that's what I'm going to talk about next. Really wish I were there to give this talk. I hope you guys are enjoying yourselves. Okay, so what is an enumeration pointed tree or an E-pointed tree? A tree in 2 to the less than omega is E-pointed if it has no dead ends, is a pruned tree, and every infinite path enumerates T. Here I can say enumerates not because we treat the paths as total objects. Now there are several variations on this definition. I took my tree to be in 2 to the less than omega. A bare E-pointed tree would be in omega to the less than omega. A uniformly E-pointed tree is exactly what you would expect. Every path enumerates T by some fixed operator. And we can even allow E-pointed trees with dead ends. So there's at least, well, I've given you 8 versions now of the notion of E-pointed tree, depending on which of these 3 Booleans you take. Okay. Uniformly E-pointed trees, those are the ones in 2 to the less than omega, are cototal and uniformly introenumerable. So this is one of the things that connects us back to what we were just talking about. And this is not hard to prove. Their proofs are compactness arguments similar to the ones that I gave above. And in fact, there's a reason they're similar. Because if you take a minimal subshift C, you look at the pruned tree T that gives you that minimal subshift. So C is the set of paths through this pruned tree T. This is all happening in Cantor space. Then T is uniformly E-pointed, right? It's given a path. I can enumerate the language, and from the language I can recover the tree. Okay, so in some sense, enumeration pointed trees can be seen as generalizations of the previous example. All right, now where do these enumeration pointed trees come from? Well, I think in the last slide I even pointed out that the definition was due to Montalban, Antonio. And he doesn't actually give them the name enumeration pointed in his 2021 book, but they appear in a proof. And so some of what I'm saying right now is actually implicit in that proof, not made explicit. But he does prove this first part explicitly. If a structure spectrum is the Turing upward closure of an F sigma subset of 2 to the omega, then it is an enumeration cone, the set of total degrees, Turing degrees. It's the set of Turing degrees above some fixed enumeration degree. So this is a spectrum of a structure. This is from his book on commutable structure theory. But it's not just any enumeration cone. In particular, it must be the cone above the enumeration degree of an e-pointed tree. And the converse holds. If you have an e-pointed tree, then, well, the paths through that form a closed set, and the tree itself can be thought of as a structure. And in fact, the spectrum of that structure is the Turing upward closure of the closed set of paths. So, so actually, this is tight. The Turing upward closure, if a structure spectrum is a Turing upward closure of an F sigma subset of 2 to the omega, then it's a cone of Turing degrees above some cototal enumeration. I haven't pointed that out yet. Above the enumeration degree of some e-pointed tree, and the reverse holds. And the same is true if we look at F sigma subsets of bare space and bare e-pointed trees. And we were a little bit confused on this point, by the way. We thought let me say, Antonio, I don't think he was confused on it. I'll speak for myself. I was confused on this point. I didn't realize there were 2 different theorems here, one for counter space and one for bare space. For a while, I didn't understand that. And conflating those 2 led to a little bit of confusion on this issue. But they really are 2 different results. And we'll see that more clearly later on in the talk. Okay, now I've already given a hint to this. I said that McCarthy's work on cototal degrees passed through e-pointed trees, and here's what he showed. An enumeration degree is cototal if and only if it contains an e-pointed tree. This is in 2 to the less than omega. That can be uniform or not. That can have dead ends or not. All four of the Cantor varieties of e-pointed trees give you the same enumeration degrees, and those are the cototal enumeration degrees. And this was, like I said, this is the stepping stone. He proved this, and from that, he did some really nice work and produced a minimal subshift from an e-pointed tree, from a uniformly e-pointed tree. Okay, so what about introenumerability? This is supposed to be a talk about introenumerability. We got some examples of things that are uniformly introenumerable, but let's say a little bit more. So given an infinite set I, let T sub I be the tree of subsets of I. This is in omega to the less than omega, right? In other words, F is a path through T sub I if and only if F is an injective function whose range is a subset of I. So I definitely want the paths to not repeat elements. I want it to be subsets, not, what would you call that? Sub-bags? I'm not sure. Anyway, note that T sub I has no dead ends because I assumed that I is an infinite set. And in fact, if I is introenumerable, then T sub I is bare e-pointed. This is really easy to see. And if it's uniformly introenumerable, then that's also uniform. Then it's a uniformly bare e-pointed tree. And why is that? I mean, I wrote proof, but it's really just an observation. If you take a path through T sub I, well, that enumerates its own range. That range is a subset of I. All subsets of I are enumeration above I, possibly uniformly if we took uniform introenumerability. And of course, I itself is enumeration above T sub I. Given I can enumerate the tree of subsets of I. So every path enumerates the tree of subsets uniformly if you took I to be uniformly introenumerable. All right. So what do we have? Cototal is equivalent to uniformly e-pointed. Uniformly e-pointed, or cototal, whatever, however you want to think about it, implies uniformly introenumerable, and uniformly introenumerable implies uniformly bare e-pointed. Degree-wise. All of this is meant to be degree-wise. So this is basically where, and all these implications turn out to be strict, but we don't know that yet. This is where the work with Junle, Josiah, and Maria started more or less. And this picture I have here is basically where it finished. We knew that cototal, equivalent to Cantor E pointed in all variations, implied uniformly introenumerable, implied uniformly bare E pointed, and we didn't know what else was going on there. And we wanted to understand, well, for one thing, whether any of those implications were reversed. I've already told you they don't, and I'm telling it to you again, all the solid arrows in this diagram are strict. The red arrow here is open. We don't know if introenumerable implies uniformly bare E pointed. I strongly suspect that it doesn't. And I should say this, everything else in the diagram is resolved. And if this arrow is false, if introenumerable does not imply uniformly bare E pointed, then, I do have it written down here, then these dashed arrows are also strict. And so that would actually resolve everything in the diagram. And we're still working on that. We're working on separating introenumerable from uniformly introenumerable and bare E pointed from uniformly bare E pointed. But this is where things stand right now. In fact, we would have been working on that, except everyone left Madison for this conference. Okay, so most of this stuff in the diagram you should recognize from what I've said already, but not this bit up here. Well, okay, this bit, yes, but not hypercototal. So notice that while all the Cantor versions turn out to be the same, we have at least of E pointedness turn out to be the same. We have at least two types of bare E pointed degrees. If you allow dead ends, then you get this thing called hypercototal, and it doesn't matter whether the trees are uniformly E pointed or not. Otherwise, there's one or two other notions where you don't allow dead ends. And I suspect these are distinct, because I suspect all four of these notions here in the diagram are in fact distinct. Let me say a little bit though about this hypercototal, about the stuff at the top of this diagram. It'll turn out not to be so closely related to the things I care more about, which are the things between cototal and bare E pointed. So Sanchez in 1978 introduced hyperenumeration reduction as a higher version of enumeration reduction. And it fits nicely into an analogy between computability theory and higher computability theory that you've probably seen. You've probably seen that CE relative to an oracle is analogous to pi11 relative to an oracle, in the same way that Turing reduction is analogous to hyperarithmetic reducibility. And that is going to be in the same way that enumeration reduction is analogous to hyperenumeration reduction. For example, remember that A is Turing below B if and only if A join A complement is enumeration below B join B complement. Well, we have the same thing in the higher setting. That A is hyperarithmetically reducible to B if and only if A join A complement is hyperenumeration below B join B complement. So think of it as the positive version of hyperarithmetic reducibility. Yeah. Okay. So of course, now that we have that, we can just start, we can redo everything in terms of hyperenumeration reducibility. I'm not going to talk about that, but hypercototal is exactly what you would expect. A is hyperenumeration below A complement. Well, and one of the things that Sanchez proved, by the way, maybe the main result of his paper was that not every set is hypertotal. And that implies that not every set is hypercototal. I guess actually he proved that not every degree is hypertotal, but it's true for hypercototal as well. Anyway, an enumeration degree is hypercototal if it contains a hypercototal set. And here's a slight surprise. This is equivalent to only containing hypercototal sets. If two sets are enumeration equivalent, then one of them is hypercototal, the other one is hypercototal. That's not true of hyperenumeration degrees, of course, but it is true of enumeration degrees. Okay. sort of following the same type of work that McCarthy did, it can be shown that an enumeration degree is hypercototal if and only if it contains a uniformly bare e-pointed tree with dead ends. So that was was already shown in the diagram you saw. Some facts, though, to kind of compare this notion to the other notions in the diagram. All pi 101 sets are hypercototal because they're in the least hyperenumeration degree. Pi 101 sets are trivial with respect to hyperenumeration reduction. The same way CE sets are in the bottom degree in the enumeration degrees. On the other hand, it can be shown that no 3 generic is enumeration equivalent to a bare e-pointed tree. So hypercototal, which is equivalent to bare e-pointed with dead ends, very definitely does not imply bare e-pointed, because there are arithmetic sets that are not bare e-pointed. They do not have bare e-pointed degree, but all hyperarithmetic, in fact, all pi 101 sets have hypercototal degree. So these classes are, or I guess it's one class, they're equivalent. This class is way too big to really be of that much interest in this talk. It is of interest, but it's not interesting when you're thinking about these classes down here. All right. So our main results are much more difficult separations than what I just sketched. There's a uniformly introenumerable set that does not have cototal degree. So showing that this arrow is strict. And really, the title of the talk was promising more or less this theorem, or I guess not promising that theorem, but promising to tell you what the relationship is between cototal and uniformly introenumerable. And that's what it is. The other theorem is that there's a uniformly bare e-pointed tree that does not have introenumerable degree. And that theorem gives us the strictness for both of these arrows. Right? We are going to discuss the first of these two theorems. I should say, though, the second theorem was actually the first one to be proved. And I think it's a little bit more complicated. So I will talk about the first theorem. But what I wanted to say was that Josiah Jacobson Grocott, who is Maria's graduate student, was really the hero on this work. He drove this work, and he came up with a breakthrough that gave us this theorem. And I'm not sure that we'd have either of these theorems without him. So I just want to put that name out there, mispronounce that name, put it out there, and suggest that in a couple of years, if you're looking to hire a postdoc, you should definitely consider him. He's very, very smart. Okay. So now the theorem that I said I would talk about. And how much time have I given myself? Oh, too much time. I've given myself too much time to talk about this theorem. So I just want to apologize to all of you for what's about to happen. I'm about to spend 3 slides telling you the forcing notion that we used to prove this theorem. It's not so bad, but it does have a lot of parts. Okay, so the theorem we want to prove is that there's a uniformly introenumerable set that does not have cototal degree. We build this set by forcing. And before I can even tell you what that forcing notion is, I want to tell you about the enumeration operator that we fixed. So we fixed an enumeration operator, and that's the enumeration operator that will witness that I is uniformly introenumerable, that every infinite subset of I is enumeration above I itself. Uniformly, and this is the operator that does it, this psi. And this psi behaves well with respect to finite sets. It takes the empty set to the empty set. If S is finite, then psi of S is finite. And if psi of S is a subset of T where both S and T are finite, then there's an X such that psi of S union X is exactly T. So I can grow psi on a finite set however I like. Okay, there's a lot of room for for us to maneuver in our construction. Psi is very abundant in this sense. This previous property extends, in fact, to finite sequences of pairs of sets, but it can't do so arbitrarily, because it still has to be an enumeration operator. It still has to be the fact that if X is a subset of T, then psi of X is a subset of psi of T. But within that restriction, I can give a subset of pairs of sets Si and Ti, such that psi of Si is a subset of Ti, and I want to grow Si, I want to grow psi of Si union some X, I want that to be Ti. Again, there's some consistency requirements that have to be met. We sort of sidestepped that the way we actually wrote it up. But yes, it psi is lets you basically have as much control as possible in growing the image of finite sets as you grow the sets. I hope that makes sense. Anyway, so we fixed this psi. All right, and now the forcing notion. A forcing condition has the form G. Let me tell you what G is going to be. G, which is a set of good numbers, it's a finite set, and it will be, all these numbers are going to be in the introenumerable set we're building. B0 through Bk, for some k and omega, these are all bad sets. Every n in any of these sets, these are also finite sets, is bad and will be kept out of our introenumerable sets. Now, the big question you should have immediately is, why do you need so many bad sets? And I will talk about that at the very end. And then there's an L, which I haven't said anything about. Let's say that A is the union of all the good set with all the bad sets. So it's all the numbers that we have any opinion about. L is going to be a map from A cross a power set of A to omega times 2 union this funny symbol. Okay. And let me tell you what this L is doing. Well, first of all, L of n comma c is telling us how close we are to adding n to psi of c. If L of n comma c is 0, then n is actually in psi of c. It has to be in psi of c, and vice versa. If n is in psi of c, then the labeling, then c labels n 0. C thinks that n is actually in its image, and is right. On the other hand, well, other than this funny symbol here, which I'll come back to in a moment, it's giving you an ordinal. And that ordinal is some measure of how close we are to adding n to, well, not psi of c itself, of course, because psi of c is some fixed finite set, but as we grow c, how close we are to adding n to that superset of c, psi of that superset of c. Now, this funny symbol here will be a placeholder for finite numbers of an indeterminate but presumably large size. So I'm going to call this pseudo-finite. They're things we want to think of as finite numbers, but we don't want to specify which finite numbers they are. And we order omega times 2 union pseudo-finite, and much the way you would expect, with pseudo-finite being below all the infinite numbers and above all the finite numbers. And I really like this symbol because, look, if you're over here to the left of it, it looks like the infinity symbol. So you're going, ah, yes, that's infinite. And if you're over here, it does not look like the infinity symbol. So it just perfectly fits in where it belongs. Bigger than all the finite numbers, smaller than all the actual infinite numbers. Okay, so we have this labeling of numbers by sets. And if that labeling ever hits 0, that number has to go into psi of the set. That labeling is fixed, though. We're not changing the label for n comma c. Well, to be clear, we're changing the label for supersets of c. So let me, or I'm not making this clear, am I? Here's what I'm trying to say. If D is a proper superset of C and N is any number in A, then usually what's happening is that L of N comma D is strictly less than L of N comma C. So the labeling, this ordinal labeling, almost ordinal labeling, has to get smaller and smaller as we grow the finite set. So N gets closer and closer to being in psi of the finite set as we grow the finite set. There are two exceptions, of course. If we hit 0, well, we can't keep getting smaller. And if we hit pseudo-finite, we're also allowed to stop getting smaller. But there's going to have to be some restrictions on the use of this pseudo-finite symbol. Because the pseudo-finite symbol allows us to sidestep the fact that omega times 2 is well-founded. The labeling should be forcing us to put N into psi of, any large enough subset of G, the good set, really. And that works as long as we're in this situation where, as we grow the set, the ordinal labeling is dropping. But if we're not in that situation, we're in trouble. Okay. Pseudo-finite is only allowed if N is worse than any element of C. That's the rule. And so if I let A sub j be the good set union the bad sets greater than bj, so for example, A sub k is G itself, then I get the rule that L of N comma C is, if L of N comma C is pseudo-finite, then it must be the case that, like I said, N is in B sub j and C is a subset of A sub j. All the elements of C are to the left of, are less bad than N. Might even be good. And the reason is that, for example, if C is actually a subset of G, I don't want N to go in to psi of C. I want something to prevent me from forcing N into psi of C. And in fact, if C is, say, a subset of G and N is in one of the bad sets, then Ln of C must be greater than or equal to pseudo-finite. So I'm not forced to put it in. And this is true, in fact, if C is any set of numbers less bad than N, then C better not be putting N in to psi. Okay, psi 6 and 3, as I've already said, no bad number can be in psi of G. And there's one more condition which I won't even talk about. It's just a transitivity property for finiteness or pseudo-finiteness. There are various ways in which you could want this ordinal, pseudo-ordinal labeling to have some internal structure, some nice kind of consistent internal structure. This is the least we needed to get the proof to work out, basically. We just need this property that says if D thinks everything in C will go in a pseudo-finite amount of time, and C union D thinks N goes in a pseudo-finite amount of time, then D thinks N goes in a pseudo-finite amount of time. It's a technical property, and we need it, but I'm not going to try to defend it. Whereas everything else, other than the fact that we have way too many different bad sets, I think is pretty easily defensible. All right. So those are the forcing conditions. We say that P prime extends P if the good set has gotten bigger. Well, at least G prime is a superset of G. It doesn't have to get bigger. G prime is a superset of G. All the bad sets in P are the same. So the initial segment of the bad sets in P prime has to be the same as the bad sets in P, and then it can have some more bad sets. So we're not actually growing bad sets when we extend. We're just adding new bad sets. And the labeling in the extension is exactly the same where it was already defined in P. So P prime's labeling agrees with, is compatible with, extends P's labeling. Okay. none of that's terribly surprising. If F is a filter, then we let I sub F be the union for all P and F of GP. Remember, the things in the good sets were the things I said I was going to put into my uniformly introenumerable set, and this is where I'm doing it. And the things we'd have to prove the theorem are that if F is sufficiently generic, then I sub F is infinite. And this, this uses the choice of psi. There's a little bit of a technical proof here that you don't ever get stuck. You can always extend a condition and add some more stuff to the good set. Our conditions are complicated enough that that requires proof, and it requires the freedom that psi gave us. I sub F is uniformly introenumerable. This is actually pretty straightforward. All this ordinal labeling stuff, I mean, yes, we had this pseudo-finite marker, but it's not allowed to be used in the case that we care about. If you have any infinite subset of good elements, of I sub F, well, some finite subset of that, and any infinite subset of I sub F and some other element in I sub F. And well, then any finite subset of that infinite set gave n some label. It has to be an ordinal. As you grow that finite subset, those labels have to drop, and eventually n goes in. So, I mean, this part is basically what we built everything for, modulo all the extra complications, and the extra complications are to show that I sub F does not have cototal degree. And this is where we use that sequence of bad sets. And this is also where I ran out of energy to write this talk. So the next slide, I just drew. So why do we have the sequence of bad sets? All right. Well, let's say we start with any condition P. And we extend it to P0 to add some new X, some new element X. And this X is going to be used for some diagonalization, right? So first we think, well, what if X is going to be in the introenumerable set that I'm building? Okay. Can I get an easy win diagonalizing on that X? I'm not even going to tell you exactly what I'm trying to do here. I'm trying to prove that the introenumerable set is not cototal, so I have to diagonalize against some reductions that would witness it being cototal. Okay, so can I diagonalize with X as my witness and get an easy win? If not, I want to lock that in. And that's my condition P1, locks in some information about that failure. Now, the next thing I can do is I can take that X out of my good set, and I can put it and maybe some other elements that were in my good set in P1. I shove them into a new bad set. Here I've just said that I put X into one of the bad sets, but in fact, it's going to be in a new bad set in Q0. So less bad than all the old bad sets, but still bad. So now I'm saying X is not going to be in the introenumerable set. I'm playing the other side of the game. What if I don't put X in my introenumerable set? Can I get an easy win then? Can I get a diagonalization with witness X? Q0, by the way, and this has to do with actually some specifics in how I put X into the good set of P0. Q0 is not going to be an extension of P0. It can't be. I took X out of the good set, but it will be an extension of P. So if I can't get an easy win there, I extend it to Q1 to lock in the fact that I didn't get an easy win. And now I want to put X back into the good set. I want to dump X and maybe some other stuff that's currently bad back into the good set. And I can do that because I had the sequence of bad sets that went from, so I had my good set and then my somewhat bad set, somewhat more bad set, somewhat more bad set, and it got worse and worse as I went off to the right. So the sequence of bad sets, the fact that the bad sets on the right treat the bad sets to the left of them as if they were good with respect to how the labeling works, means that however I did this extension from Q0 to Q1, I can now take all that, I can take the new bad set that I put X in and all the stuff that's less bad than that, dump it back into the good set and get a condition R. that extends P1, but has at least the stuff that was good in Q1, good in R. And basically that's where I get a contradiction. If I didn't get an easy win from P0, I didn't get an easy win from Q0, I locked in both of those losses, combined those two into one condition, that gets me a contradiction. I know this has been very vague, but it's this ability to basically take X out of the good set, make it bad, do some extension, and then put it back to get an extension of my P1. That's important. This is not novel to this forcing argument, but it's a nice feature to have. It's the key to our argument that, like I said, that I sub f does not have cototal degree. So I apologize for getting to this slide, basically. And I thank you all for listening.
Thank you very much. So is there any question? So yes, Stefan.
Joe, quick question. Where do you use the infinite labels? What's the role of them? I mean, I see the finite and the pseudo finite, but where the infinite used?
Oh, well, I mean, that's actually, so if you go back to here. So when I put X into the good set, I have to, in P0, I have to have some labeling. I have to label X somehow, right? With respect to the stuff that was already in the good set in P. Now, that labeling has to be infinite, because otherwise I can never move X out of the good set. Because once something's labeled finitely, it's inexorably going to go into psi. So I label X with respect to the stuff that's in P, so that basically this Q0 can still be an extension of P. I mean, that's a good question. Really, though, once you have a finite label, you might as well just go in immediately. So those infinite labels are important. But I'd say that at least one place that comes up is what I was just saying, that X is labeled infinitely with respect to every subset of the good set of P. And that lets me define this Q0 to be an extension of P and take X out of the good set. Does that work? Does it help?
Okay.
Stefan? No, okay.
Sort of.
Okay.
Okay, any other question? No, in the online audience? Okay, so let's thanks again the speaker.